section 6.1. So what we've talked about so far is 5.5, and then we skipped ahead to about half the material out of 6.2. So we're jumping around a little bit here. We will eventually return to 6.2 at the end of this analysis of integration techniques. The last topic in there is trig substitution, and I want to hold that off until the very end. So today we're going to talk about 6.1, and on, let's see, this is Wednesday, so on Monday we will talk about 6.3, which is partial fractions, and then hopefully go back to 6.2. So today is 6.1, then 6.3, and then 6.2 as a second half of 6.2. Okay. So today is 6.1. 6.1, the topic is integration by parts. Alright, so what is integration by parts? Well, integration by parts is a technique for finding antiderivatives, and the idea is that if you might remember when we were first talking about U substitutions, that U subs are a way to somehow undo a chain rule question. So in other words, if the original function was a composition of functions and you took a derivative, in order to undo that derivative, where you had to use the chain rule, we used the U substitution to work it backwards. Now, it didn't always work out completely 100%, clearly. I mean, sometimes you had to massage it a little bit, and there were some extra constants that you had to deal with. But the idea is that a U sub somehow undoes the chain rule. Well, integration by parts somehow undoes the product rule. Now, the connection to the product rule is not quite as immediate as the U substitution is to a composition of functions, but eventually we'll see how integration by parts is connected to the product rule. Alright, so I'm going to tell you the formula for integration by parts, and we're going to use it, and then we'll figure out where that formula came from. Alright, so here's our formula for integration by parts. If U and V are differentiable functions, and so I might think of U as U of x, U is some function of x, and V is also some function of x. So if U and V are differentiable functions, then the integral of U dV is equal to U times V minus the integral of V du. And this is our formula for an indefinite integral. And if I have boundaries on my integral, then I have the integral from a to b of U times dV is equal to U times V, evaluated between a and b, minus the integral from a to b of V du. Okay. So I throw the boundaries every place I possibly can if I have boundaries on my original integral. Alright, so this is a formula that you want to get to know. The integral of U dV is equal to UV minus the integral of V du. Now, one of the first times that I ever taught Calc 2, there was a student in my course who had taken some calculus in high school, and she had learned an interesting way of remembering this formula, and she raised her hand and she shared it with the classes, so I'm going to share it with you right now. And the way to remember it is ultraviolet minus super voodoo. So you've got UV, ultraviolet, minus super voodoo. Ultraviolet minus super voodoo. Okay, so it is very important that you do know this formula, because this is our tool that we'll need to solve any sort of problems that use integration by parts. So I'd like you to turn to one of your neighbors. Good. ahead and turn to your neighbor, say hello. And I would like the person who is closest to this door to say the formula for integration by parts to the neighbor who is farthest away from this door. Ready? Go.
UV minus super voodoo.
UV minus super.
Alright, stop. If you didn't say it yet, you took too long.
Dracula.
Okay. Now swap your roles. The person who's farthest away from this door, say it back to your neighbor. You have 5 seconds. 1.
Oh yeah, ultraviolet minus super voodoo.
Stop. That's all the time you got. Okay. So let's take a look at an example. So again, right now this formula has poof dropped out of the heavens, and we're just going to use it, and then we're going to talk about where it comes from. So here's our first example. The integral of x times cosine x dx. All right, now we are eventually going to use integration by parts on this particular integral, but I want to talk about some other things that we want to cross off the list first. So for example, we have multiplication here. It's x times cosine x, which means that I cannot separate this integral into 2 separate integrals. Okay? If it was addition, I could, but multiplication, I cannot. Additionally, thinking about a u substitution, which we've been practicing those for a couple of days now, if I wanted to do a u substitution, I might choose a u to be cosine x, but that's not going to work because I don't have a derivative that involves a sine x that won't cancel. The other option would be to let u be equal to x, and that doesn't do anything for us. All that does is change all the u's into x's and nothing else changes. Okay? So this is not a good candidate for a u substitution. So at this point, without integration by parts, we don't have any tools to analyze this particular integral. Okay, so here's what we're going to do. And this is a technique that I use off on the side. You do not need to set up this sidebar the way that I do, but you do want to have this information off to the side. Now, when I look over here at my formula, the integral of u dv is equal to uv minus the integral of v du. There are several pieces that are involved here. I've got a u, I've got a v, I see a du, and I see a dv. And so I like to set up this chart over on the side. All right, now the idea is that we want to take this integral and somehow match it so that it looks like the integral of u times dv. So I want to have the integral of x cosine x be the integral of u dv. So in order, oops, I forgot the dx in the end here. So what I need to do here is I need to do some matching. I need to determine which portion of the left-hand side here is my u and which portion is the dv. Now in this first problem, I'm just going to tell you what we're going to choose. After that, we'll talk about why I chose it. Okay. In my choice here, I am going to allow my u to be the x. Unlike u substitution, it's perfectly legitimate to let u be equal to x. In integration by parts, it's totally legal. Okay, so since my x is the u part, then whatever is left over must be the dv, which means that the cosine of x times dx is my dv. All right, so my job here at the very beginning is to identify what the u value will be, and whatever's left over will be the dv. Okay, so now I'm going to go back to my problem. I've got the integral of x cosine x dx. And the idea is that we have the integral of u dv is equal to uv minus the integral of v du. So I can write down what u is, I know what that is, but I don't know what v is. Okay? So I need to fill in the rest of this chart. So some information, for example, I know that dv is equal to cosine of x dx. To go backwards, essentially what I'm going to do is I'm going to integrate. I'm going to look at the antiderivative of dv is v. The antiderivative of cosine of x is sine x. So here, to get my v, I need to find the antiderivative of cosine x. Ben?
Is there a plus c? No. 'Cause we're not-
So that's a good question. Technically there is a plus c, but similar to when we're working with the u substitutions, this is kind of an intermediate step. So I'm going to wait and just have one global plus c at the end. Okay, so I took my antiderivative to get v. On the other hand, I'm eventually going to need a du. So to get du, well, I can think about u being equal to x. And so my derivative, du over dx, is equal to 1. And so du is equal to 1 dx. So the way I can think about this is take the derivative of both sides, and immediately in my head I'm going to move that dx over to the right. Okay, so these are the four pieces that I need. So the integral of x cosine x dx, integral of u dv, is equal to uv, so u is x, times v, which is sine x, minus the integral of v sine x du. du is 1 times dx.
You just put dx though, right? You don't need to put the 1.
What's up?
We don't need to put the 1.
No, you don't have to put the 1 here at all. Just the dx is fine. Okay, so we've now written down uv minus the integral of v du. And so now we've got some things done. We've got x times sine x. And now I've got the antiderivative of sine x dx. So integral of sine x dx, antiderivative of sine,
Cosine.
yeah, negative cosine. Okay, so minus a negative cosine x. And so my final answer I can leave just as x times sine x minus a negative cosine x plus c, or I can write it as x sine x plus cosine x plus c.
I have a question.
Yeah, ask what?
So, to get the v, you went from the integral of dv.
Yes. So we do an antiderivative to go from dv
So
up
just
to
the
v.
antiderivative of dv to v.
Yep.
And the derivative.
And for u, we have to take the derivative to get dv.
Okay.
And so that's why I set it up in the chart this way, so that taking the derivative is stepping down, taking the antiderivative is stepping up.
Okay, makes sense.
So, by the way, you can double check that your final answer there, if you take its derivative, then you should get back the original integrand. So let's double check that. And so our final answer was x times sine x plus cosine x plus c. And so if I take the derivative of this, then, well, I have to use the product rule here at the beginning. Product rule showing up. Okay. First times derivative of the second, plus second, times derivative of the first. So we have x cosine x plus sine x times 1, minus, so plus derivative of cosine is negative sine. We have minus sine x, and then the derivative of the c is 0. So the sine x and then minus sine x cancel, and we're left with x cosine x. And so we're very happy about that, because once we took the derivative of the final answer, we came up with what we started with. Okay. So are there any questions on the process of what we did here?
Didn't before you showed us the one, when you took the integral of 1 and turned it to x or u?
Oh, so, wait, ask that again?
Before you showed that when you take the integral of 1,
Yes.
it turns back to x or u.
Yes.
I was wondering why you dropped the 1, if that was the case.
This one here. So,
Here.
so I'm literally writing this down as I'm replacing du literally with 1 dx. So that one is multiplied in with the other things, it's not 1 plus. So I wouldn't be then taking the antiderivative of 1 in there because it's multiplied together with everything else.
So it's either subtracted that you.
Yeah. Then it's when there's a 1 that's standing all by itself, then your antiderivative of that is u or x or whatever variable you're talking about. But if it's multiplied with everything else, we treat it as a constant that gets carried along.
So like for picking your u and everything, I mean, is it just always like the single whatever's in front?
So
The
that's a really
simplest-
good question. What are good
simplest.
rules of thumb for choosing the u? Okay, and so the rules of thumb for choosing the u, and this is exactly what we're going to talk about next, is very different from u substitution. U substitution, the u that we want to choose is, rule of thumb, the inside function, the function whose derivative somehow shows up in the other portion of the integral. For integration by parts, our strategy for choosing u, how do we choose our u for integration by parts? There's an acronym, and the acronym is LIATE. If you ignore the I, then it's late, but the I can sometimes show up, so you maybe remember it as LIATE. So this is our acronym, and here's what the letters stand for. The L stands for logarithm. So things such as, for example, natural log of x, or natural log of x, the whole thing squared, something like that, anything that involves a natural log. I stands for inverse trig. So if you see something like arctangent of x, for example. A stands for algebraic. So something like an x squared, 5x to the 10th, things like that. T stands for trigonometry. So things like sine x, cosine x, tangent x, things like that. And E stands for exponential. So things like e to the x would be an example of exponential function. And so what this, yeah, your question?
It just seems like that list includes everything we see.
It does. And so there's a priority in this list. So this is hopefully all the types of functions that you'll for the most part see. And the idea is that your choice for u should go from top priority to low priority. So if you see a natural log in an integral that you're looking at, you say, bam, that's what I want u to be equal to. Okay? And if you don't see any logs, we move on to inverse trig and we move down the list from there. So this is our ordering. So for example, on the problem that we looked at as our first example, x times cosine of x, I see an x, so that's my algebra, and I see cosine of x, which is trig. And so in terms of my hierarchy here, algebra comes above trig, and so my choice for u was the x. Now, just as a comment, and if you choose to ignore this comment, totally legit. Okay? One of the reasons that logarithm is number 1 on the list is because the u, that value, we take the derivative of that. And we know what the derivative of natural log is. If we don't choose u to be the natural log function, then the natural log would fall into the leftovers, into the dv, and we'd have to take an antiderivative, and we don't know an antiderivative for log. So that's why log is number 1 on that list. Okay, so let's look at another example. Alright, our next example is antiderivative or integral of x to the 6 times natural log of x dx. Okay, so again, we are talking about integration by parts, but I want to talk about if this jumped out from a dark alley and we weren't in the middle of section 6.1, you wouldn't know to use integration by parts right away. So you might have as a thought process, okay, can I do any simplifying? No. These are multiplied together. I cannot split up the integral. U substitution is not a good option because things are not really going to go away from me so well. I'm not going to be able to cancel things. So then I say, okay, integration by parts. My formula is uv minus the integral of v du. So the integral of u dv is equal to uv minus the integral of v du. So the idea is that we want to choose our u. So I'm going to make my table. So I have u and v in my first row and du and dv in my second row. And choosing my u, I look at my acronym LEAT, and first I say, do I see any logs? And the answer is yes. I see a log up there, so that's going to be my u. U will be natural log of x. And everything else, other than my u, gets lumped into the dv. So the leftover parts, the x to the 6th, and the dx, are my dv values. All right, are there any questions about what we set up here? Okay, so now I'm going to work over here on the side. The derivative of u is du, derivative of natural log of x would be 1 over x dx. And my antiderivative, well, I'm going to add 1 to the power and divide by that new power, so I have 1/7 x to the 7th plus c, but it's an intermediate step, so I'll wait until the end to put the plus c on. And so now, my integral of x to the 6th times the natural log of x dx is equal to uv, so I've got natural log of x. That's my u. My v is 1/7 x to the 7th minus the integral of v 1/7 x to the 7th du, which is 1 over x dx. Okay, are there any questions on filling in the pieces of ultraviolet minus super voodoo? UV minus integral of UV.
Does that dx have to be on at the end of 1x dx?
Yes, so this part right here. So what we're really thinking of here is, I'm skipping a step by saying that really, I'm taking the derivative of both sides, so I really have du over dx is equal to 1 over x, and then I'm immediately multiplying both sides by dx, because I want to get the du by itself.
Okay.
Okay, other questions? Yes?
Because there's another product over there, are we going to have to do it again?
So that's a good question. So 95% of the time when you're working with integration by parts and you write down your new integral here, you're going to get stuff that looks a little bit messy. Our first example did not have that happen, but here we have something that looks a little bit messier here. 95% of the time, the step before we continue with this integral is going to be to simplify. So once you write this down, next step is to simplify if possible. And so as I rewrite this, I'm going to go ahead and rewrite the beginning part as 1/7 x to the 7th times the natural log of x. And in terms of things that I can do over here, one thing I can do is I can bring the 1/7 in front of the integral sign. And then we have x to the 7th times 1 over x, so we can do some canceling here. And we end up with the integral of x to the 6th dx. Okay. So at this point, whenever you write down uv minus the integral of v du, most of the time you're going to have to simplify here before we analyze this new integral. So no calculus went into the step I just did, strictly algebra simplification. Okay, so now that we have this simplified, now I look at the integral of x to the 6th dx, and I know how to find that antiderivative. And so, actually, I can probably just fit this final answer down here. we've got 1/7 x to the 7th times the natural log of x minus 1/7 times 1/7 x to the 7th, and then plus c. And if I want to, I can multiply those 1/7ths together to give me 1/49 x to the 7th. Okay, final answer. Any questions about that one? Dennis?
So like you were saying with the simplify, you never got to do the product rule like he was saying. It would always be like, would there be a case where you'd have to do it again?
So sometimes this integral can still be hard, and yes, there will be times when we might have to do integration by parts a second time. But in this case, you don't want to have to do that. In this case, you want to say, can I simplify it?
No,
And if
no.
the answer is yes, simplify first.
Yeah, but there could be special cases
Absolutely.
where you have to.
Yep. Yes. Okay, questions or other questions or comments? Yes.
When we're integrating on the table, will we ever have to do U subs within that?
Within this table up here?
Yeah.
Yes, that could happen. So for example, here you might have something like dv is equal to cosine of 2x dx. And so you might have to do an aside over here to calculate the integral of cosine of 2x dx and maybe use a u substitution to find the original function. So yeah, absolutely, those things can definitely happen.
Not in this class.
Yeah.
It might happen on your homework tonight. Okay, so
Jeez.
now I've told you about the formula. I've just straight up barfed it on the board and said, here's the formula, and we've used this formula now. But it's not really fair to do that. So the next question is, where does this formula come from? And I think that this is a really good question for you to take home and tell your neighbor about, tell your roommate about. So you want to be able to explain where this formula comes from. And for those of you that have never had me in class, that means that there's a chance that something like, where does this formula come from, could be on the next exam. Okay? So tell your neighbor about it, share it with your roommate, your spouse, your children. If none of them want to listen to you talk about calculus, then talk to your dog. All right, so where do we get this formula? All right, now when I wrote down the formula, I said, we need to have two differentiable functions, u and v. Okay, so suppose we have two differentiable functions, meaning functions where we can find their derivatives. So two differentiable functions, u and v. And I'm thinking about u as a function of x and v as a function of x. But I'm never going to write v of x and u of x. I'm just going to write them as u and v. So we have two differentiable functions. Now, I told you that somehow this integration by parts somehow undoes the product rule or is related to the product rule. So what I'd like you to do right now is I'd like you to turn to your neighbor and remind them what the product rule says.
First times the anti.
A show.
Yeah, but it's
Either way.
tomato.
All right, so anybody have a neighbor who had immediately knew it off the top of their head? Your neighbor did, what did she say?
First times the second plus the second times the first. Or first times the derivative of the second plus the second times the derivative of the first.
Okay, first
Or vice
times the
versa.
derivative of the second plus
Or
second
vice
times
versa.
the derivative of the first. All right, now there's other ways to say that. You can talk about f's and g's and g primes, and that's fine as well. So what we're going to do is to look at the derivative of u times v. So remember, u and v are both functions of x, and we are going to take the derivative with respect to x. And so we have our first, which is u, times the derivative of the second. Derivative of v will be dv over dx, plus second, that's v, times the derivative of the first. Derivative of u is du over dx. Okay, so this is what the product rule says in this particular case. Now, what I'm going to do next is I'm going to take this equation that tells us about the product rule, and I'm going to integrate both sides with respect to x. So integrate with respect to, that's WRT, with respect to x. And so on the left side, I have the integral of the derivative of u times v dx. And on the right side, I have the integral of u times dv over dx plus v times du over dx and a dx at the end. So in other words, I'm doing the same thing to both sides of my equation. I'm putting an integral sign and a dx, and I'm enveloping the left side with the integral and the dx, and I'm doing the same thing on the right side. Okay, so now I'm going to take this equation here and I'm going to simplify. Now, the very first thing that I can do in terms of simplifying is on the left side. If I have the antiderivative of a derivative, well, they cancel each other, derivative and antiderivative, and so what I'm left with on the left side is u times v. And over on the right side, well, I have two separate functions inside the integrand that are combined with a plus sign, which means that I can separate this into two separate integrals. So I've got the integral of u times dv over dx times dx plus the integral of v du over dx times dx. Okay. Anybody see anything that we can do now to do some simplifying? That figured out in your head? Wait here. The dx's and things? Yeah, the dx's, we've got a dx in the denominator and the numerator in both cases here. And so take a look at what this leaves us with. We have uv is equal to the integral of u dv plus the integral of v du. And if you look back at that formula that we started with, this looks very similar to that. All the parts are there. We just have to move them around on the equation. And so if I subtract the integral of v du from both sides, then I'm left with uv minus the integral of v du is equal to the integral of u dv. And that right there is our integration by parts formula if I flip it across the equation. And so finally, the integral of u dv is equal to uv minus the integral of v du. All right, so that formula that I just barfed on the board at the beginning of the hour really came from using the product rule. So if I wanted to explain where this formula comes from, I would start by saying, here are my two functions, u and v. I'm going to multiply them together and take their derivative. I'm going to take a derivative, then I'm going to integrate and do some simplifying. So you should take this home and talk to your spouse, talk to your friends, tell somebody about where integration by parts comes from. Okay? If no one will listen to you and your dog won't even listen to you, take a whiteboard marker and write it on your bathroom mirror so that when you're brushing your teeth you can look at it and think about it. Okay?
So it's just the product rule says you just times the function, take the derivative.
Yep, multiply the function, take the derivative, then integrate and simplify. And it gives you that cool formula. Okay, all right, questions or comments about that? Other questions? Okay, so let's take a look at least one more example. We'll see if we have